Everyone, in this video we're going to go through an introduction to the hypothesis testing process. I'm going to follow the 5 steps outlined in our text. So step 1 is to state the hypotheses. So this means we need to figure out what is the claim that we're trying to make or trying to test, as well as the null hypothesis. So my example here is a statistics teacher wishes to study the amount of time students in his course spend studying each week. He thinks that the average should be more than 6 hours per week. So the statement here that he thinks the average should be more than 6 hours is kind of the claim that we're making. So the question is this average time spent studying? This is talking about the mean of a population, the population being students in this statistics course. Is that mean greater than 6? Right, so my claim is that it's greater than 6. That may or may not be true. Now, the null hypothesis is going to be a statement of equality, something where, there's no difference, no change. In this case, the null hypothesis would be that the mean is just equal to 6. Here's another example. A hospital studies the survival rates for patients who suffered cardiac arrest during the day versus during the night. The administration is concerned that survival rates are worse during night shifts because of reduced staffing. So here we're comparing survival rates for 2 different groups. A survival rate or any kind of rate is really a proportion. This would be some sort of percentage or what proportion of patients survive after their cardiac arrest. So we're going to be comparing 2 different proportions. The survival proportion for patients who are there during the day versus there during the night. So we would typically write this as something like P1 and P2. I'm going to let day be the first group and night be the second group, although you could assign those however you like. But in this case, the concern here is that the survival rates are worse, meaning that the survival rates are lower for those who have their cardiac arrest at night. So the claim here is that P2 is smaller than P1. The null hypothesis in this case would be that the 2 survival rates are the same, so P1 equals P2. So we can make claims about lots of different parameters, whether that's a mean or a proportion, a standard deviation. In our class, we're going to focus on a mean, a proportion, or 2 means, but there are lots of different types of hypothesis tests that you can do with the same general process. All right, step 2, once we've identified what claim we're testing and our null hypothesis, we need to figure out what type of test statistic we're going to compute. And I have a little table here of the 3 that we're going to focus on in our class, but there are lots of different test statistics that are linked in the text as well, depending upon what type of claim you're looking at. So in the first case, we had a claim about one mean, that the mean is supposed to be greater than 6. And for this, we're going to look at the sampling distribution of a mean, which would be the student t distribution. This is something similar to what we saw in the interval estimates section. And we're going to calculate a test statistic, and this is the formula that we would use. This is essentially like a z-score calculation, but for the sampling distribution of the sample mean. So you'll see we have the sample mean here. That's the individual value for the sample in this distribution. We have what's called mu0, which means the mu value associated with the null hypothesis. So in our previous example, that would be 6, but it's based on whatever our null hypothesis is. And then in the denominator, we have this s over root n, which should look familiar from our interval estimates. This is similar to sigma over root n, which comes from the central limit theorem. This is the standard deviation of the sampling distribution. So we're calculating what would be sort of like a z-score, although we're not using z here because this is a t distribution rather than a normal distribution. You can use a normal distribution for claims about a mean under certain conditions, particularly if we know the population standard deviation, or if your sample is large enough, the normal distribution will be essentially the same as the t-distribution. But in any case, we would compute a test statistic, which is sort of a placement of our sample information relative to the possible outcomes of the sampling distribution under the assumption of the null hypothesis. So that's kind of a mouthful, but all three of these test statistics, I have the formula for the test statistic when you're looking at a proportion or a claim about a proportion, and the test statistic for looking at the difference or comparing two different means, and which distribution we're using for each one of these. So some of these elements should be similar to what we've seen in the interval estimates section. But again, in all of these cases, we're placing our sample value, for example, the sample proportion, in the sampling distribution for sample proportions. So after we've identified the test statistic and computed it using some sort of sample information, we do need to decide on a significance level, and you could do this either before or after step 2. But this alpha value, in many of your homework problems, this will just be given to you, but this is where we determine what allowable risk we want for a type 1 error. So a standard significance level or alpha value would be 0.05, or sort of like a 5% error rate. The smaller you make your alpha, the smaller the risk of a type 1 error, but the larger the risk of a type 2 error. So we don't want to make it too small if we're concerned about getting a type 2 error. But the standard, again, 0.05, we sometimes will see 0.01 or 0.1. This is sort of similar to how our interval estimates could be 95% confidence or 90% confidence. This is just kind of the flip side of that. And the reason we need a significance level is that we need some kind of benchmark for how strong our evidence needs to be, right? How much evidence for or against our claim do we need before we can make a particular conclusion? All right, step 4 is to collect our sample data, compute that test statistic that we identified earlier, and then calculate the p-value. And this is kind of the meat of the computational part of the hypothesis testing process. So I included an image here. This is adapted from an image from Wikipedia. I have the authors on the screen here. And we're looking at, again, a sampling distribution. This could be a t-distribution or a normal distribution for the examples we've looked at, although different types of hypothesis testing also follow different distributions. And we're looking at where does our test statistic fall. In this case, that is represented with this capital T, and it's showing a spot kind of towards the right-hand side of the curve, but that test statistic could fall anywhere depending upon what sample we see. So where does our sample information fall in the sampling distribution? Was it higher than expected, lower than expected, in the middle, extreme, not extreme? Where does it fall? Now, in the sampling distribution, we are assuming that the null hypothesis is true, and this is key. So we're saying if the null hypothesis is true, where does our sample value fall? Where does it lie? In this picture, the sample is, or the test statistic is above the peak, so it's a little bit higher than what we would expect, but not necessarily super high. So we're asking, how extreme is this test statistic in the sampling distribution? The actual p-value is the green shaded area here. That is the probability of seeing our test statistic or something bigger in this picture, which is a measure of how unlikely, how unusual this test statistic is. Now, this particular picture, because we're taking the test statistic and then finding the area to the right, This would be what we would see for a right-tailed claim like p is greater than 0.9 or mu is greater than 25, or in the example we saw, we had mu greater than 6. If your claim is about something being greater than a certain amount, then you're going to find the p-value as being the area to the right. If you have a left-tailed test like p is less than 0.9, then we would expect our sample statistic to be on the left-hand side, otherwise we really don't have evidence for the claim, and we would find the area to the left. You'll see that you can also have two-tailed tests, in which case we're finding an area kind of in both tails. So we need to use our sample statistic and the distribution that applies to the sampling distribution we're looking at to measure that p-value. And finally, based on the p-value, we're going to make a decision. So this little diagram here has our starting assumption. Hypothesis is formed around H0. So we're assuming that H0 is true, and then we're calculating that p-value. And the question we're asking here is the p-value small? If it is small, that would represent, scooching back to this other picture, if the p-value is small, that means that our test statistic is quite extreme. It's quite either significantly high or significantly low, depending upon what direction we're going. So if the p-value is small, we would say it doesn't really seem like H0 is likely to be true. Our sample is very unusual if the null hypothesis is true. And this comes back to our significance level, because we need some kind of criteria of what does it mean to be small, right? Is a small probability 10%, 5%, 1%, 0.1%? So the criteria here we use is if the p-value is less than alpha, less than our significance level, we will reject the null hypothesis. When you reject the null hypothesis, you're saying that there is evidence for the claim. So whatever that alternative claim was, that the mean is higher than a certain number, or the P1 is less than P2, or whatever the claim was we were making, that alternative to the null hypothesis, we do have significant evidence for that. If the p-value is not less than alpha, and it might still be somewhat small, but not small enough for us to be confident in saying that H0 is not true, or we think it's not true, then we fail to reject the null hypothesis, which really just means that maybe the null hypothesis is true, maybe not, but we don't really have evidence against it. So this outcome really represents a lack of evidence. Sorry, my handwriting is getting bad here. Not enough evidence to support the claim. The sample results that we got were not extreme enough to be inconsistent with the null hypothesis, which means that sample is not good evidence for our claim. So just an example to see how this might play out. So previous research in psychology shows that college students have an average stress score of 20 on a particular stress measurement. And a researcher wants to test whether students participating in an 8-week mindfulness meditation program will have a reduction in this stress score. So we want to look at the students who participate in this program, that is our population, and what is their stress level compared to general college students. So the claim here would be something about the mean stress score of the students in this who have completed this program, and the claim would be that this stress level is less than 20. This also means that our null hypothesis would be that the mean is equal to 20. That would represent that students in this program are not, they don't have any change in their stress score. The program is not helpful in reducing stress. So in order to test this claim and see if it's true or not, we need some sample data. So here's our imaginary sample data. So the researcher recruits a sample of 50 students. The 50 students is our sample. And their stress scores after completing this program have a mean of 16.3. So this is the mean of the sample. or X bar, and a standard deviation of 5.6. So this would be the sample standard deviation. So before I do any kind of calculations, I want to think just intuitively about what is this actually evidence for the claim. So the claim here was that the population mean of people who completed this mindfulness meditation would be less than the general stress score of 20. That's what we hope to be true, or what the researcher hopes to be true. The mean in our sample is in fact less than 20, so this is plausible evidence to support that claim. But we have to be a little bit cautious here because the standard deviation is 5.6. So how far away from 20 really is this? Is this far enough away to be strong statistical evidence that the population value would be less than 20? Or did we just by chance get a sample whose mean was below 20, but maybe a different sample would have a mean above 20? The way we judge that is by assuming that the true population mean is just 20, looking at the sampling distribution according to that assumption, and saying, where does our X bar fall in that sampling distribution? It's, I guess it's lower than expected, right? Because 20 would be the expected value of our sample mean if the population mean is 20. It's lower than that, 16.3, but how much lower? Is it way over in the tail over here, or is it just to the left of the peak? So here again are our steps. We have already stated the hypotheses. Our claim is that mu is less than 20, and the null hypothesis is mu equals 20. I would need to select the test statistic for a single mean claim. This is going to use the t-distribution. And the test statistic would look like X bar minus mu 0 over S over root n. In this case, our X bar was 16.3. Mu 0, the assumed mean, is 20. That's coming from the null hypothesis. S was 5.6. over square root of n, that is the sample size, root 50. So I could plug this into some kind of calculator and calculate my test statistic. In this case, I get a test statistic of negative 4.67 approximately. So this is giving me a sense of where this sample falls in the hypothetical sampling distribution. Setting the significance level, I likely would just use the standard 0.05 here, unless there was some reason that I was particularly concerned about either a type 1 or a type 2 error. In most cases, this will just be given to you, but you could alter this in certain scenarios. Then calculating the p-value, this is going to be looking at our t-distribution and the test statistic, negative 4.67 that we calculated. This is a left-tailed test based on our claim. We're claiming that the population mean is less than 20. So I would expect that my test statistic would be to the left, and it is. We have a negative t-value here. The p-value would be the area to the left of that point. You could calculate this in Excel or with a t-distribution table or some other method. And in this case, the p-value is quite small. It's about 0.00001179. This is certainly less than the significance level, less than alpha. This tells me that this result is actually quite unlikely or quite extremely low if the null hypothesis is true. So we would reject the null hypothesis. It doesn't seem like the population mean is 20. It seems like the population mean is likely less than that because our sample mean came out so far below expected. So we have enough evidence to support the claim that this 8-week meditation program does lower the stress level of these college students. So our conclusion might look like something like there is sufficient evidence that their stress scores are lower than 20. They're meaning the people who completed the program. Now, something we should be asking, this is telling us that there's strong statistical evidence for the claim, but we might want to know, well, how much lower are they, right? Are they only a little bit lower than 20, or are they significantly lower? That's something that you can answer with an interval estimate. But our hypothesis tests are really aimed at getting sort of a yes or no answer to a particular claim, or at least how strong is the evidence for or against our claim. We'll have some other videos with more details on the actual computations on these and for different types of claims, but that is it for the hypothesis testing process. Thanks for watching.